Hello and welcome. My name is Dr. Mark Taylor, and this is Delaware Tech Physics 111 Lesson 4, the first lesson of Unit 2 on forces and energy. So we're starting with forces in this lesson. We're going to briefly do a little reminder of velocity versus acceleration. We'll have a quick thought experiment about velocity and acceleration. Then we'll talk about how vectors are added. Vectors depend on direction, so we'll talk about the addition of those. Then we'll talk about the definition of force itself, as well as the units of force and the fact that it is a vector. Then we'll discuss a concept called net force, also known as sum of forces or sum of all forces, and we'll do the big takeaways about how forces and motion are related. And then the last section of this will be covering briefly the three laws of motion. These are Isaac Newton's three laws of motion. The first law, also called the law of inertia. The second law, called the law of acceleration. And the third law, called the law of action and reaction. So quickly, let's just remind ourselves what velocity is and how it differs from what acceleration is. So velocity and acceleration are two of the most commonly confused and interchanged ideas, especially when describing motion. And before we get on to the forces, we have to make sure you understand the distinction between these two, and this will help you understand the acceleration as it relates to forces, specifically net forces in this course. So to remind ourselves, velocity, which we abbreviate with a lowercase v, is the rate of change of position over the change in time. In other words, it's the change in position divided by the change in time. Change in position is also known as displacement, so it's the displacement over time. Velocity really tells you what the motion of the object is. It tells you which direction it is going and the speed at that direction. So the units we typically use for velocity are meters per second, and we have to give it a direction, and for most calculations, that direction will be either a positive or negative sign. If we're talking about horizontal motion, to the right is positive, to the left is negative. If we're talking about vertical motion, up is positive, down is negative. Acceleration, abbreviated with a lowercase a, is the rate of change of velocity over time. So the change in velocity means a change in either the speed or the direction, and we commonly would say it's a change in motion. But when we say change in motion, we really mean change in velocity. And the units we use for acceleration are typically meters per second, which we usually write as meters per second squared. And it is also a vector, so it also requires a direction, and typically we'll use a plus or minus sign. So, quick thought experiment here. We've got three situations. And for each situation, I want you to think about the direction of the initial velocity. So in other words, at the very beginning of what's happening, which direction is the initial velocity? Part B, what is the direction of the acceleration? In other words, is it pointing to the right? Is it pointing to the left? Is it up or down? Is it some other direction? Maybe there is no acceleration. Okay. And C, how do you know what the acceleration is? What information is provided in the problem? All right, so number one says a car continues to travel north at 50 miles per hour. Okay, well, it says continues to travel. That's your big clue. Continues to travel is telling you the velocity is constant. And it is north is the direction. So if we just say north, that is our direction of our velocity. And we know that the initial velocity, the value of that is 50 miles per hour. I'm going to write miles per hour this way, miles per hour, instead of our classic mph that we're used to writing. Right? What is our acceleration? Well, continues to travel means it's not changing its velocity. So by definition, since the velocity is not changing, that means acceleration is 0. So our clue that tells us acceleration is 0 is literally the phrase continues to travel. It's not changing its direction. It's not changing its speed. Therefore, it's not changing its velocity. If the velocity is constant, then that means the change in velocity is 0, and that means acceleration is 0 as well. All right, let's look at number 2. Number 2 says, try to get this moving here. Number 2 says we have a start position, it's the dot on the left, and these arrows tell us the direction of and magnitude of the velocity at various positions that the object is moving. So our start position shows us that the object starts here and is moving with this velocity, that size, speed in that direction. And then the object is moved to here, and you'll see the speed is a little bit greater, and then the speed is a little bit greater, and then it finally ends at this position here. Well, we know our initial velocity is whatever that first arrow is. It's that. That is our initial velocity. Our acceleration is a positive value. It's increasing the velocity to the right. It's making the velocity go up. And so we know the acceleration is positive because the velocity is increasing to the right. It's becoming more and more positive. Now, sliding down here, we look at number 3. Now, number 3 is a representation of a velocity versus time plot. These are plots that we've done before, and the solid bars are the axes. So we see we have a velocity axis and we have a time axis, and the actual plot of this curve is this line here. You'll notice we start at this point and we end at this point, and the velocity is increasing, starting from a negative value and then finally ending with a velocity of 0 at some time on this axis. So what does this mean? It means the initial velocity is some negative value. It's this value right there. And over time, the velocity is increasing. It's becoming more towards the positive range, but it actually increases until it gets to 0. So it's increasing. So we see that the velocity is increasing. It's becoming less negative, excuse me. I can say becoming less negative. And that means that a positive increase in velocity means our acceleration is a positive value. And that's it for our thought experiment. So moving on to the next part of this, brief reminder of what vectors are. Vector is a measurement that has a magnitude and a direction. A magnitude just means it has a size, usually a number value, usually with a unit, though we have a couple properties that are what we call unitless properties that you'll learn about in this unit actually. But most of them have a number and a unit, but they also have a direction. Vectors have to have a direction. Scalars do not have a direction. So you can think of vectors as arrows. The bigger the arrow, the greater the magnitude, and the direction of the arrow tells you the direction of that vector. So there's one arrow like that, and then we have a smaller magnitude arrow pointing in that direction, or we have a huge magnitude a vector pointing up in this case. So we use arrows to represent the vectors. All right. So We know that position is a vector, and position is used to calculate displacement. So that's a vector too, but not distance. We use displacement, or change in position, to calculate velocity. So that's a vector. We use the change in velocity to calculate acceleration. So that's a vector. And in this unit, you'll learn that you use acceleration, or forms of acceleration, including g for gravity. We use those to calculate force. So force is also a vector. It has a direction. And there are many, many, many types of forces you're going to learn about. Weight is a type of force. Tension is a type of force. Friction is a type of force. We have something called applied forces. That just means you're pushing or pulling something. Those are all forces. They all have directions. They all have magnitudes. And so vectors are not like scalars in terms of how you add them up. Scalars, they're just a magnitude. You add up. If you had a bunch of masses are in kilograms. Let's say you had 2 kilograms and you had 5 kilograms. You needed to add them up. You just add 2 kilograms plus 5 kilograms. You get 7 kilograms. Scalar addition is easy. Vector addition can be a little tricky. You have to keep account of the direction of every vector. Some vectors will be in the same direction. Some vectors will be in the opposite direction. Some vectors will be in completely different directions, perpendicular or in an angle. Now, in this course, you need to know how to add vectors that are in the same direction or in the opposite direction. To do anything more where things are perpendicular to each other at an angle, that requires trigonometry to do those, and that's beyond the scope of the course. We'll briefly mention some of those tools, but you're not responsible for them. Okay, so let's look at some simple examples of vector addition. In this first example here, we have 2 identical vectors pointing in the same direction. Well, if they're in the same direction, you really can treat them like scalars. You just add a 5-unit vector to the right to another 5-unit vector, and you can think of this as just writing them head to tail. Here's where you start, here's where you end, and then you add another vector to that, right to the tail, right to the head of the last vector. Let's see if I can get this to stop doing that. And you just draw the next vector, and it tells you where you end up. Well, the sum of those vectors is a 10-unit vector to the right. But what if the vectors are in opposite directions? Well, if they're opposite directions, that means they're going to start canceling each other out, either partially or completely. Well, in this simple example, we have a vector to the right with a value 5 and a vector to the left with a value 5. Well, they're going to completely cancel each other out. Whatever the first vector did of moving from here to here, if you add a vector in the opposite direction with the same magnitude, you're just back to where you started from. So the sum of these 2 vectors is 0. Well, how do you do that mathematically? Well, you can treat vectors that are to the right as positive numbers, so we can call this a positive 5 vector, and we can call this one, since it's pointing to the left, a negative 5 vector, and we just add positive 5 plus negative 5 together, we get 0, and that's our sum. Now, the example below is just pointing vertically instead of horizontally, but it behaves exactly the same way. And we can treat up as positive, so we could say that this is the same as adding a positive 5 vector to a negative 10 vector, since it's pointing down. We have 5 pointing up, 10 pointing down. That's like a positive 5 plus a negative 10. When we add those together, you get a negative 5. Well, how do we represent negative 5? Well, we represent it with a down vector of length 5. And you can see that if you add these 2 together, if you added the length of this in this direction to the length of this in this direction, they will partially cancel out. They'll cancel out this much of the 10 vector, but what's left over is this much. and that is the 5-unit vector pointing down. So that's how you do vector addition, and the easiest way for you to think about this, I hope, is if it's horizontal and to the right, we'll call it a positive. If it's horizontal to the left, we'll call it a negative. If it's vertical and it's pointing up, it's positive. If it's vertical and pointing down, we'll call it negative. And this way, we won't assign a positive and negative sign until we know the direction of that vector. And this will help us when we're analyzing vectors like forces. So what is a force? Well, you can think of a force simply as a push or a pull, a continuous push or a continuous pull. Once the push or pull is done, once something stops pulling or pushing, the force is over. But while the force is happening, forces cause changes in motion of an object. What does that mean? It means they cause changes in velocity of the object. That it's not that they cause velocity. They don't cause velocity. They cause changes in velocity. And it's extremely important that you understand the distinction here. Just because you see motion does not mean there's a force. If you see a motion changing, if you see a velocity changing, and velocity changing means either a change in speed or a change in direction, if the velocity is changing, that is the definition of acceleration. Acceleration is any type of change in velocity, either a change in speed or a change in direction. Now, it's both. The math that you're going to do in this course, it's rarely going to be involving changes in direction. Most of the math you're going to be dealing with will be changes in speed, but it is important you understand that a force can cause changes in speed. That means up or down, makes it faster or slower, or it can change the direction entirely. Okay, so any change in velocity is an acceleration. Forces cause acceleration. So motion does not mean there's a force. Just because you see something moving doesn't mean there's a force on it. I cannot stress this enough. Motion does not mean there's a force. Force is all about something changing. Not that there is a motion, but that the motion is changing. And the same is true of acceleration. Acceleration and force are not about motion. They're about changes in motion. That's how you know there is a force acting on something or a net force acting on something. In other words, after you add up all the forces, what force is left over, that if there is anything left over, that will cause the object to change its velocity. It will cause the object to change its acceleration, which means it'll change its speed, it'll get faster, it'll get slower, or it will change its direction. Okay, so how do we measure forces? Well, forces are measured in a unit called newtons, and we abbreviate newtons with a capital N. And this is the unit in the metric system. It is also the unit in the international standard system, the SI system, and that's the unit we'll be using for the vast majority of time. Now, if you were working in the imperial system like most Americans do, typically the unit for force in the imperial system is the pound. This is the unit you use for weight all the time. And you might say, well, wait, that's the unit for weight, not for force. Well, there are many types of forces. And if you look down here, here's just some of the types of forces. Weight is a type of force. Friction is a type of force, also known as frictional force. Tension in a taut string or rope or cord or wire, that's a force. There are applied forces where somebody's pushing or pulling something. There are many, many different kinds of forces. And we'll learn about a couple others later on in the semester as well. Gravitational force is also known as weight. So weight is a type of force. And all forces in this class will be measured in newtons. Well, what is a newton? Well, we have to back up and say How do we calculate forces? Well, one of the ways we calculate forces is to measure the mass and multiply it by some acceleration. And that acceleration, in the case of weight, that acceleration is the acceleration due to gravity, g, but it could be any other acceleration, so some type of acceleration. Well, the unit of mass that we use is a kilogram, and the unit of acceleration, you already know, is the meter per second squared. Well, when you multiply kilogram times meter per second squared, we just call that thing a Newton. So we don't keep writing meter per second, kilogram meter per second squared. We don't keep writing that, we just say Newton. So if it's a force, any type of force, it's in newtons. And remember, force is a vector, so we represent it with arrows all the time. We might have a big arrow pointing up, a little arrow pointing down, an arrow to the right, an arrow to the left. There might be a diagonal arrow. The bigger the arrow, the bigger the magnitude of the force, and the direction of the arrow tells us the direction of the force. Vector forces are another kind of vector. So don't confuse your units here. The unit of mass is a kilogram. It is not a Newton. The unit of mass is a kilogram. We abbreviate kilogram, little k, lowercase k, lowercase g, kilogram. Forces, it's always in newtons. Now, you might say, well, wait, I thought mass and weight are the same thing. No, mass and weight, I know in everyday English they might mean the same thing. In sciences, they do not mean the same thing. They are very different things. Mass is how much matter. It's the amount of matter in an object. The more matter in the object, the more mass. And all matter has mass. Solids have mass, liquids have mass, even gases have mass, even plasma. The stars are made of plasma, they have mass. The air that we breathe is a gas, it's a mixture of gases. That has mass, and we measure mass in kilograms. We measure forces in newtons, and the distinction between weight, which confuses a lot of students, between mass and weight. Mass is how much matter there is. Weight is how much force is on that mass because there is gravity. If there's no gravity, there's no weight. So if you're on the moon, your weight is much less. Your mass is exactly the same. If you had a mass of, say, 50 kilograms on the Earth, you'd have a mass of 50 kilograms on the moon. Your matter didn't change when you went from one place to another. The amount of matter is exactly the same. Your gravity changed, and we'll show those formulas later, but your weight will change. So forces can depend on a number of different things. Your mass depends on how much matter is in you. Okay. So before we get to these takeaways here, we have to discuss a concept of net force, also known as the sum of forces. And so a net force, which we abbreviate with the symbol F sub net, or the sum of forces, which we use this sigma symbol, this uppercase sigma from the Greek alphabet, means the sum of. You're adding up all the different forces. Some of them might be in the same direction, some might be in opposite direction, some might be perpendicular, some might be in some other direction. When you add them all up, and some things get canceled and some things get added together, some things are subtracted, whatever's left, that's your sum of all forces, and we call that the net force. It's the same way as when you get a paycheck and say you've earned $500 and you think, oh, I'm going to get a paycheck for $500. But then you remember, oh, right, the company deducts money for my federal tax, my state tax, my health insurance, my Social Security, whatever is in there. Well, after they do all those addition of your original salary and all the subtractions of your deductions, and you get your final pay is called your net pay. So you adding up all these positives and negatives, some things add to your pay, some things take away from your pay. Whatever's left is your net pay. Well, it's the same thing with forces. your net force is the same as the sum of all the forces, keeping track of which things are positive, which things are negative, etc. So when you add them together, whatever is left after certain things are canceled out, that is your net force or your sum of all forces. And we tend to do these sums just in the horizontal direction first, and then we do them in the vertical direction separate. We keep them separate to simplify our math. So let's take a look at some examples here. And these examples tend to be either horizontal or vertical directions. So example A says a downward force of 100 newtons plus an upward force of 100 newtons gives a net force of what? Well, let's just draw it. It'll be easier to see. Once you see, you'll know the answer here. You have a downward force of 100 newtons. And then you also have an upward force of 100 newtons. Well, you can imagine if somebody is pushing you down with 100 newtons of force and somebody else is pulling you up with 100 newtons of force, the net force on you is going to be zero. These two forces will cancel out completely. So your net force is just simply zero. Part B, a force of 500 newtons to the right. So we have 500 newtons to the right. And a second force of 300 newtons to the left gives a net force of what? Well, the 300 newtons will partially cancel the 500 newtons. And if you want to figure it out mathematically, it's easier to turn these numbers into positive and negatives. You can treat the 500 Newton force as, since it's going to the right, as a plus 500 Newton force. And the force to the left of 300 newtons, that's a negative 300 Newton force. Remember, to the right is positive and the left is negative. Well, when you add these up, you get a net force of positive 200 newtons. Well, another way to say that is 200 newtons to the right. And I'll just circle R for right. The third example says a push force of 50 newtons to the right. So you can imagine some object and somebody's pushing it with 50 newtons to the right, is balanced by a frictional force. So we haven't talked about frictional forces, but that's the force of the object and between the object and the floor. It's because these objects aren't perfectly smooth. There's a certain amount of friction, and we'll go over this in more detail next week or the next lesson. But if you have another force pointing in the opposite direction, and we don't know what that force is, well, what would it require to balance it? Well, it would require exactly the same magnitude force, but in the opposite direction. So it must be a 50 Newton force to the left. And we can think of this as a positive 50 force, 50 Newton force, balanced by a negative 50 Newton force. Okay, so if we look at number 2 here, it says forces cause changes in motion, which really means changes in velocity. A net force, meaning we add up all the forces, whatever's left that hasn't been canceled, can change an object's motion in 3 ways. Okay, what this means is it can change its velocity in 3 ways, or it can cause acceleration in 3 ways. So remember, velocity is both speed and direction, so it can change the velocity in one of 3 ways. Well, the 3 ways are the speed increases. Write this in here. Speed increases. Speed decreases, of course. But velocity isn't just speed. Velocity is also direction. So the third way it can change velocity is by changing direction. And you can think of these three ways that acceleration can happen, these three ways that velocity can change, as what happens when you drive a car. Speed increases, this is your gas pedal. Speed decreases, this is your brake. And change direction, that's your steering wheel. So while we usually think of the accelerator as the one pedal that we also call the gas, to a physicist, there are three accelerators in a car: the gas pedal, the brake, and the steering wheel. All of these change velocity in one way or another, increasing speed, decreasing speed, or changing direction. Very important to understand that acceleration comes in these three forms. Now, for calculations purposes, we'll have you be doing the first two, but in a more advanced physics course, you might be looking at changing direction as well. All right, so let's look at number 3 here. Net force and constant motion. In other words, net force and constant velocity. Now, there are two ways that you could have constant velocity, two major categories. You can have it constantly zero, that is, the object is stopped. We typically call this at rest. So this is what you see in a question when it says at rest. All right, that's the object stopped. That object has a velocity of 0 at that point. And if it's that way for the whole problem, that's a constant velocity of 0. But you might also have a constant velocity of something not 0. It could be a constant positive value, so say if it was horizontal going to the right, or a constant negative value going to the left. All right, so but both of these are constant velocity. To a physicist generally does not care whether the velocity is constantly 0 or constantly something else. It's still constant in any case. And when the velocity is constant, I'm going to write that over here, there are a number of ramifications as a direct result of this. Constant velocity means the initial velocity and the final velocity are the same velocity. And that means the change in velocity is 0. Well, remember, acceleration is the change in velocity over the change in time. If the change in velocity is 0, then the acceleration is 0. And what we'll learn later in this unit is that acceleration and net force are tightly related. And if acceleration is 0, the net force is also 0. Let's see if I can write that better than that. There we go. Get that there. Okay. So the net force. So any one of these things, if any one of these things is true, you know it's either stopped or in constant motion. That means that the final and the initial velocity are the same. That means there's no change in velocity. That means there's no change in velocity divided by time, which means there's no acceleration, and therefore there's no net force. You'll notice having no net force does not mean there's no motion. It means there's no change in motion. So this only happens, having a net force of 0 only happens if there are no forces or if the forces happen to cancel out. And we say that this can only happen when the forces are balanced. In other words, they are in opposite directions and they have equal magnitudes, so they cancel each other out. And therefore, the net force is 0, and the net force is the sum of the forces, so that is also 0. And here it just says the net force is 0. So any one of these things that I have circled here, if any one of those is true, all of them are true. Any one, all of them. All right. And if we look at number 4 here, the direction of the net force versus the direction of the acceleration. Well, net force causes the acceleration. Once we look at all the different forces on an object, we decide what's canceled out and what's left. Whatever's left, that's the net force, and that will cause an object to accelerate, a mass to accelerate. And that acceleration is only being driven by the sum of the forces, by the net force. Therefore, the direction of the acceleration is always, 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 always in the same direction as the net force. So if you have a net force that's going this way, that will also be your direction of your acceleration. If your net force is this way, your acceleration will also be in that direction. It says nothing about the size of the acceleration or the size of the net force. It's just saying the two directions are always, always, always identical. Okay, let's continue on with something that I feel is really central to much of your understanding about how physics works. And these are three laws that were devised by Isaac Newton. They're referred to as Newton's three laws of motion. They each have a name, but we frequently call them the first law, the second law, and the third law. But the first law is also called the law of inertia. And inertia is really a way of thinking of mass of an object. It's not just how much matter it has. Inertia is really telling you the tendency to resist any change in motion or any change in velocity. In other words, if a force is put on a certain object that has inertia, it's going to be hard to move that object. It won't be impossible, but the more the inertia, the harder it is to move. And this property is the exact same property as mass. So the more mass an object has, the more force you have to impart on that mass to get it to change its motion, to get it to accelerate. So we go to the rule itself. The rule itself says an object that is at rest will remain at rest, and an object that is moving will continue to move at a constant speed and a constant straight line. That's just another way of saying at a constant velocity, if and only if the net force on that object is zero. Well, what does that mean? That means if the object's not moving, it'll stay not moving. If the object is already moving in a straight line with a constant speed, it'll keep doing that forever unless there is some net force on it that is not zero, that there is some force changing its motion. All right? If there's no net force on an object, I'm reading the translation now, if there's no net force on the object, it'll continue to do what it's already doing, whether it has a constant velocity of zero, meaning it's at rest, or a constant velocity of something else, meaning it's moving in a straight line with a certain speed. And that is Newton's first law. Okay? But remember, inertia really is just another way of thinking of mass. And we use, for the mass units, we use kilograms. We tend to use kilograms for inertia as well. It's really the same thing. It's two different ways of thinking of the same thing. Mass is the amount of matter. Inertia is the amount of resistance to movement by a force. All right. So here are a couple of questions that relate to Newton's first law. A spaceship is traveling in deep space. In other words, it's far from any planet or moon or star that has gravity. And the spaceship is moving at 30,000 kilometers per hour. It's pretty fast. What's happening when the ship suddenly runs out of fuel? So the ship is traveling 30,000 kilometers per hour. That's roughly 20,000 miles per hour. It runs out of fuel. What will happen? A, the ship instantly comes to a stop. B, the ship gradually slows to a stop because the fuel is necessary to maintain motion. C, the ship begins to drift randomly because there's no longer a force acting on it. Or D, the ship continues in the same direction with the same speed of 30,000 kilometers per hour. Now, if you remember Newton's law, Newton's first law says if an object is at rest, It'll continue to be at rest if an object is moving with a certain speed and direction, in other words, with a certain velocity. It'll continue to do that forever unless there's a force on it. Well, the force was the force of the engines that had fuel, but now there is no force. There is no fuel. The engines aren't doing anything anymore, and now the ship is just continuing to move at that speed, at that direction, essentially forever, unless it encounters some other force, like the gravity of some star that it's approaching or planet or whatever. So the answer is D in this case. Remember, at this point, there are no forces acting on the ship. It has a large inertia. It's going to keep doing what it was doing. Unlike nearly every science fiction movie you've ever seen, where a spaceship runs out of fuel or the engine's cut out, and they say, oh my God, we're coming to a stop. No, they're just going to keep going at the same speed they were going, unless they're using some special magical drive that we don't have the science for nowadays. All right, number 2, a bus driver slams on the brakes and the passengers suddenly lurch forward. Why? All right, this has happened to all of us in a car or a bus or a Uber or a truck. We're driving along, someone hits the brakes, and everybody moves forward. Why? A bus exerts a forward force on the passengers when it stops. B, gravity pulls passengers forward when the bus decelerates. C, the passengers continue moving forward due to their inertia. D, a braking force acts more strongly on the bus than on the passengers. Okay, well, let's think about Newton's first law. What's going on? You have a bus going in a certain direction at a certain speed. That means everybody in that bus is also moving in a certain direction with a certain speed. The second the bus slams on the brakes, the bus stops moving with that same speed, but all the passengers keep moving with the same speed, and they lurch forward. So it's not that the passengers are lurching forward, it's literally that the bus is slowing down relative to how fast the passengers are moving. So it appears the passengers are lurching forward. And the same thing happens if the bus turns left, everybody sways to the right. Well, that's because we were going forward and the bus turned into us. So the answer here is that the bus continues moving forward. The passengers continue moving forward due to their inertia. The bus is continuing to move forward due to its inertia as well, but it is not going forward as quickly, so we appear to move forward relative to the bus. So the answer in this case is answer C. Number 3, an object is moving at constant velocity. Which of the following must be true? Okay, now remember, constant velocity can mean two things, so we have to think about it. A, no forces act on the object. B, the net force on the object is 0. C, the object has 0 acceleration and 0 velocity. D, the object must be moving horizontally. Well, if the object is moving at constant velocity, that could be one of two things. It's either moving at a constant velocity of 0, which means it's not moving, it has no velocity, it has no acceleration, or it's moving either positive direction, negative direction, some diagonal direction at a constant speed and constant direction. But again, because it's constant, there is no acceleration. So C says it has 0 acceleration. Well, that's true every time, but it doesn't necessarily have to be a 0 velocity. It could be some velocity, just not changing that velocity, so the acceleration is 0. So we can cross off C. A says no forces act on the object. Well, that could be true, but it's not that it must be true. Yes, if you have no forces acting on an object, it will continue to either be at rest, which is a constant velocity of 0, or it will continue in a certain direction forever unless some force acts on it. So while A could be true, it's not always true. And the reason why it's not always true is, what if you have two forces that happen to be opposite each other with the same magnitude? They're equal and opposite each other on the same object. They have to be on that same object. Well, that object is not going to have any net force on it. The net force will be zero, and therefore no net force will be on the object, so therefore no net acceleration will happen on the object, and therefore the velocity will not change. So B absolutely has to be true, and D, the object has to be moving horizontally. You know, the object could be moving in any direction at all, up, down, left, right, over there, over here. It doesn't matter what the direction is. The net force on that object has to be zero, and the net force being zero means either there are no forces on it, or all the forces cancel each other, and there's nothing left to change the movement of the object. So D is not true either. Okay, let's look at Newton's second law of motion. This is also called the law of acceleration. Sometimes it's called the law of force and acceleration. But the point of this law is to relate the net force to the acceleration of an object and the mass of its object. And the second law is really a formula. It says that the net force on the object is equal to the mass of the object times the acceleration of the object. In other words, if you have a lot of different forces on an object, force from one side, another, from the top, from the bottom, whatever, and you only look at forces on that object. We never care about forces from that object, only on that object, okay? We figure out what cancels each other out, and we determine our net force. That's the sum of the forces after everything's canceled out. What we know is that if we know the mass of that object and we know the net force of that object, we can easily calculate the acceleration of that object, because the net force is equal to the mass times the acceleration. And rearranging that, that means the acceleration we see on an object is always equal to the net force, the total, the sum of all the forces on the object, divided by how much mass that object has. Plain and simple. So if you know any two of these, you know the third. And in this unit, you're going to frequently be given a number of different forces. You're going to have to determine the net force, and then knowing the net force that you just determined and the mass, you should be able to calculate the acceleration on that object. When the net force on the object is zero, that means the forces are balanced. That means there's no net force, so there's no acceleration. If the net force is not zero, that means the forces aren't canceled out, they're not balanced, they're unbalanced. So that means there is some net force to drive acceleration on an object. It might not be a very impressive acceleration, it might be a positive acceleration, it might be a negative acceleration, but there's going to be some acceleration if there's some net force on any object. Now, let's look at some of these proportionalities. And quickly, let's explain what proportionality means. Well, we have two kinds of proportionalities we need to talk about. There's something called just being proportional, sometimes called direct proportionality, and that says that if you have one thing, we'll call it x, if x goes up and y goes up by the same amount, like if I double x and I see that y also doubles, we say those two are proportional to one another. Anytime you talk about proportionality, you have to be talking about two things in a formula, and any other parameters, any other properties that are in the formula, you have to assume aren't changing while you're analyzing it, okay? So you'll notice in the list here of proportionalities, it always says what's constant, what we're not changing. So here we've got, if mass is constant, in other words, we're not worried about mass, we're only looking at net force and acceleration. If net force increases, what happens to the acceleration? Well, in this formula, we see that if this number goes up and we're not changing the mass, we're just taking a bigger number divided by the same mass, we're going to get a bigger acceleration. So acceleration increases. So we can tell proportionality from the formula. You just ask yourself, what happens to A if I make force net, the net force, larger? Well, acceleration is going to get larger too. If both of them get larger by the same amount, if I double one, the other doubles. If I triple one, the other triples. If I cut one in half, the other will cut in half. If I multiply the force by the net force by 2.73, I will multiply the acceleration by 2.73. Whatever I do to one, I will do to the other, always in terms of multiplying and dividing. So these are considered proportional. All right. Let's look at the second example. If the net force is constant, so now we're not changing the net force, we're changing the mass and the acceleration only. Those are the only things we're making modifications in. So that means the net force stays constant. The only thing I care about is the mass and the acceleration. So if the mass goes up, imagine you're dividing by a number, and the number initially is small. Mass is initially small, and then I suddenly make the mass big. If you divide by a small number, you're going to get a big number. So when the mass is small, I'm going to get a large acceleration. Does that make sense? Well, in physical terms, it does. If we have a certain amount of force on an object, so you don't even need to know the math, you just think about what would happen. If I have a certain amount of force I'm putting on something, and I increase the mass, what will happen to the acceleration? Well, let's say your force is you kicking a ball. That's your force. And you always kick with the same force. And you kick a little ping pong ball. It's going to accelerate a great deal. It's going to increase its speed in a certain direction very quickly. All right? So a low mass will have a high acceleration. But a high mass, now kick a bowling ball, something with a huge mass. The acceleration will be much smaller. It will decrease. And that comes right out of common sense, but it also comes out of this formula. If the mass goes up, this number will come down. All right, now let's look at the third example here. The third example says if acceleration is constant. Okay, so now the only things we're concerned about are the relationship between the force, the net force, and the mass. All right, so acceleration is constant this time. If mass increases, the force needed is what? Increased or decreased? Well, think about it. If you're doing an increased mass and you want to get the object to accelerate more, you're going to be taking two different masses, a small mass like a ping pong ball and a big mass like a bowling ball, and you want them to accelerate with the same meters per second squared acceleration. Do you need the same force on the ping pong ball as you do on the bowling ball? No, of course not. You have to have a much higher force on the bowling ball that has more mass to get the same acceleration. So the force needed is much higher, is increased. Okay, is increased. So what you see here is the force is increased. The force is increased if the mass is increased. those two are proportional also. If I double the mass, I have to double the force to get the same acceleration. But what about the second example? Mass increases, acceleration decreases. We say these two are inversely proportional. Inversely proportional. All right. And in that case, what it means is, for the second case, if I double the mass, the acceleration is divided by 2. If I increase the mass tenfold, the acceleration will decrease tenfold. They're inversely proportional. So whenever you have two things that are proportional, whatever you multiply or divide by one, you multiply or divide by the other. When they are inversely proportional, whatever you multiply by one, you divide by the other, and whatever you divide by one, you multiply by the other. One goes up, one goes down. Okay. Now, things to keep in mind with the units, and I've said this before, I'll just another reminder here. Mass unit is kilograms. It is a scalar quantity. But acceleration and force are both vector quantities, so they need directions. So technically we would have a plus or minus sign on each of those. But the units we use for acceleration, meters per second squared, and the units we use for force are newtons, which is equal to a kilogram meter per second squared. That's a newton. Okay, so let's look at a couple sample problems for Newton's second law. And I'm gonna write Newton's second law at the top so you remember it. I'm gonna write it in two ways. The net force equals the mass times the acceleration, or the acceleration equals the net force divided by the mass. All right. First question says a 3 kilogram box. Okay, right away, 3 kilogram box. You know that the mass is 3 kilograms because kilograms is the unit of mass. It accelerates with 4 meters per second squared in the east direction. What is the net force acting on the box? Well, we just take mass and multiply it by acceleration. And those of you who like these triangle diagrams, this would look like this: the net force, the mass, and the acceleration. The net force equals mass times acceleration. The net force divided by mass is acceleration. Net force divided by acceleration is mass. Okay. All right, so if we plug this in, our net force equals m times a. That's equal to 3 kilograms times 4 meters per second squared. I know we didn't include our direction. We can at the end. We get 12 kilogram meter per second squared. But we don't have to do that. We know that that is equivalent to 12 newtons, and remind ourselves that our direction is east, and that is our answer. Looking at number 2, a 30 kilogram object. Oh, it's kilograms. We know right away that's our mass. Pushed with the same force as in example 1, where our same force is a 12 Newton force to the east. What would the acceleration be? Well, acceleration equals net force over mass. That's 12 Newton force. We'll worry about the direction afterwards. Time divided by the mass, which is 30 kilograms. We take out our calculators and we quickly divide 12 by 30 kilograms. We get 0.4. And remember, newtons is really equal to a kilogram meter per second squared, but don't worry about that. You're calculating acceleration, so you know your units are going to be meters per second squared. And since the direction of the force, the net force, is east, it's important that we're talking about the net force. The direction of the net force is east, then the direction of the acceleration is east as well. And that's it. Okay, let's move to the third of Newton's three laws. Newton's third law of motion is also called the law of action and reaction. And this is probably one you've already heard in some context or another. I'll read it one way and then I'll say it another way. Whenever one object exerts a force on a second object, the second object exerts an equal force on the first object in the opposite direction. Okay, what does that mean? It means, and here's the phrase you may have heard, for every action, there is an equal and opposite reaction. And so if in a formula, we would say the force of object A on object B, and if we're looking at the motion of an object, we only care about the forces on that object. So this is a force on object B by A, and that is equal to the negative force, in other words, the opposite direction, of object B's force on object A. So the left is a force on B by A, and the right is a force on A by B, and negative because they're just in opposite directions. And whenever you have one of these forces and then another force that's in response to that, we call one the action force and we call the other the reaction force. Either force is the action force and either force is the reaction force. Just because you hit a baseball with a bat and you say, oh, I'm hitting the baseball with a bat, the bat is hitting the ball. Well, the ball is also hitting the bat at exactly the same moment with exactly the same force and just in an opposite direction. So you could claim either one is the action and either one is the reaction force. The combination of these two paired forces is referred to as an interaction, okay? And it's important we do not consider these two interaction forces to be cause and effect. One force is not causing the other effect. They happen simultaneously. That means at the exact same moment in time. There is no delay between the two. They are exactly equal in magnitude, in strength, in the size, and they are just exactly opposite in direction of one another. So this seems counterintuitive, especially if you're thinking about pushing on a wall and the wall is pushing back. You think, well, the wall can't push me back. Well, the wall's molecules are pushing you back. There is a force against it. You're pushing on the floor when you stand on it. The floor is pushing back. The molecules in the floor are pushing back. Otherwise, you would go through the floor. So Newton's third law is much more important than you might imagine. So to find reaction pairs, action-reaction pairs, you have to identify the two objects that are interacting. This thing is pushing this thing is pulling that, whatever. And then state the action force. Doesn't matter which one you state first. Object A is pushing on object B to the right. You have to include a direction. Make sure you include a direction. All you have to do is switch the two objects and switch the direction. So object A pushes on object B to the right, we'll just say that's our action. Well, switching object A and object B and then switching the direction, we get a reaction force. Object B pushes on object A to the left. So what's an example of that? Well, the next two are examples of that. The action is the Earth's gravitational pull on Elsa downward with a force of 600 newtons. That's a fancy way of saying Elsa's weight is 600 newtons. All right. The Earth pulls down on Elsa from the gravity. Well, something you might not have realized is that when that happens, you are also pulling on the Earth straight up with exactly the same amount of force, in this case of 600 newtons. It seems very weird that you're pulling on the Earth, but any two objects that are interacting with a force, in this case, the force is gravitational pull, both objects have exactly the same force on the other, no matter how big or small either object is. if there's a force between them, they both pull on the other with exactly the same amount of force at exactly the same time, just in exactly opposite directions. So that's that interaction force, or action interaction. I'm sorry, action, reaction, interaction. All right. So the last example of an interaction is Tanya pushes on the wall to the right with a force of 200 newtons. Well, you have Tanya pushing on the wall and to the right, and you have the amount of force. Well, the amount of force is going to stay the same if it's going the other way around. But now it's the wall pushing on Tanya to the left. So you just switch the names of the objects or people or whatever is doing the pushing or pulling, and then you switch the direction, but you keep the exact same magnitude of force. And that's it for the rules of Newton's third law of action and interaction. So let's just wrap up the lesson here with a few examples that you can try yourself. You have the action, I push the book down. Okay. Who's pushing the book? I am. What am I pushing? The book. So you switch the book and you. So the book pushes me. Well, if I'm pushing the book down, my hand is pushing the book down. Well, then the book is pushing back up. The second one is my hand pushes the water backward. Well, you can imagine if you're in a boat or you're in say a canoe and your paddle has fallen and you're trying to push over to shore. You might be on a raft in a pool and you're using your hands to push water backwards. Why? To drive you to move forward. So if your hand is pushing the water backwards, then the water must be pushing you. The water pushes me forward. And in fact, Newton's third law is the reason why you can get out of a pool if you're sitting on a raft in the middle of the pool. The third one, the earth pulls a book downward with a force of 6 newtons. So we have the earth and we have a book sitting on the earth. Earth is pulling on the book with a gravitational force of 6 newtons. You can say that's a downward force, so we'll call that negative. And at the same time, the book is pulling the earth upward with a force of 6 newtons. Now, the book pulls, penmanship's terrible, the earth upward with force of 6 newtons. Two things interact. It does not matter how big one is and how small the other. The force between them is always exactly the same force. And this is such a strange concept to get in your heads, but you have to accept that that's what's going on. It's just the forces are in opposite direction. Now, why doesn't it cause problems? It doesn't cause problems because the mass of those two objects is different, so they'll experience different accelerations. So, yes, the earth pulling me down, if I fall out of a building, I will fall with an acceleration of 9.8 meters per second squared. The earth will be pulled upward, but the acceleration is so tiny we couldn't possibly measure it. So that's just combining Newton's third law with Newton's second law for you. All right, and we'll stop here.